States of matter, very straightforward chapter, very easy. Most of the things we already learned in chemistry already, right? Just two extra things that you did not learn is basically what absolute zero is, which is very straightforward. We'll talk about that later on. And one more thing is basically the Boyle's law formula, which is the P1V1 equals to P2V2 formula. Everything else we have learned in chemistry already. But Zach, you know, right, of this states of matter. I think it's quite strict, shouldn't be. Anyways, just a quick recap, guys. States of matter, there are basically three states, right? Solid, liquid, or gas. It will either be evaporation, melting, or sublimation. Then it's condensation, freezing, or deposition, which we don't use. For any time we skip step from gas into solid, we'll just use the word sublimation. Easier. Okay, it's just sublimation. From gas to liquid is obviously condensation. From liquid to solid is obviously freezing and everything else. You can refer to the graph here. It's very straightforward, nothing much to explain there. I do want to talk a little bit about absolute zero though. Absolute zero, the first thing you need to know is basically how to convert degree Celsius into Kelvin. Degree Celsius is one form to measure temperature, and Kelvin is the Americanized way to learn to calculate temperature, which almost everywhere else don't use on. Everywhere else we use degree Celsius, except for America, which also uses Fahrenheit for some reason. Anyways, you need to learn this, is in your syllabus. The general formula for degree Celsius into changing into Kelvin, degree Celsius plus 273 becomes Kelvin. For example, if today I got 0 degrees Celsius, plus 273 will be basically 273 Kelvin. For example, if today I got 100 degrees Celsius plus 273 would have become 373 Kelvin. Okay? So if you look here, this is essentially 0 degrees Celsius and this is essentially 100 degrees Celsius. Ignore the 0.15, it's not in your syllabus. Ignore it. Okay? So actually there is a temperature known as absolute zero, where it is the lowest possible temperature achievable. Okay? It is so low that it is assumed that the particles, they actually seem like they stop moving. Although they seemingly stop moving, it's not 100% stop moving. They will still vibrate very, very slowly, guys. So if you want to look at the context here, right, at 0 degrees Celsius, although the temperature is freezing already, the water is freezing already, it becomes solid, right? The solid particles still vibrate at fixed position. At 100 degrees Celsius, obviously they have a lot of energy, so they'll move around like crazy. At absolute zero, which is negative, it's negative 273 Kelvin. Negative 273 degrees Celsius, which is the lowest possible temperature achievable, known as absolute zero. The particles seemingly stop, but you cannot say it stops. In your exam, they don't allow for you to say that the particles stop moving. They seemingly stop moving, means to say they will vibrate at the slowest possible vibration. Okay? So at 0 degrees Celsius, you can imagine that they kind of vibrate like this. At 0 Kelvin, right, they kind of vibrate like this. But they still move a little bit. It's just that it seemingly stops moving only. This is your answer in your exam. You have to write this. Absolute zero is the lowest achievable temperature in the universe. All motion seemingly stop, which is basically the lowest possible motion they can achieve. Okay? Anyone got any questions for this part here? Okay, good. Can you guys copy this down? This formula down? Is there anything else you need to copy here? No, yes or no?
I think just solid, liquid, gas, and then absolute zero, that's it.
Okay, but this one got a lot to copy, right? This one, I'm not going to go through it, but please do copy it down. It's the exact same thing that we did in chemistry already. Just copy this down and then let me know when you guys are done. First and foremost, initially, if I don't add extra temperature to the particles, what's going to happen is they themselves have some form of kinetic energy. So the particles will hit the wall, collide, move, collide, hit, collide, move, collide, collide, slowly, right? But as soon as I heat it up, what's going to happen is they themselves are going to gain kinetic energy, right? And when they gain kinetic energy, they'll start colliding more frequently. Collide. Now, this is important because right now, the frequency of collision against the walls of the container is much more, right? And because of that, if we think back about our pressure formula, pressure is equals to force over area, right? An increase in frequency of collision means to say there's going to be a greater force per unit area, which ultimately will increase the pressure inside the whole container. In your exam, they always ask you this, you have to write literally this answer here, right? Increase collision rate of the gas molecules against the walls of the container, increasing the force per unit area, ultimately leading to a increase in pressure. All right?
Yeah.
Copy this now. Done, Anyone not done copying it?
Then teacher.
Okay, then moving on to the next part here, which is Brownian motion. Now, in your exam, Brownian motion, right, is not what we learned just now. Just now we said that, oh, the particles will only collide against the wall, only change direction, and so on, right? In reality, that doesn't really happen. In reality, right, even before it collides against the wall, if I trace this particle here, it will move in random zigzag motions. Okay, why does it move in random zigzag motion? Is because even before it collides against the wall, right, maybe it will collide with some other dust particle, another dust particle, another dust particle, another dust particle. And every time it collides with other dust particles, it will actually change direction. Okay, this motion is what we call random zigzag motions, and they will all move at random speeds. In your exam, if they ask you to, there will be two ways they ask you. Either number one, define how Brownian motion is like, or number two, explain why the gas particles is moving in this specific scenario. Okay, if they ask you to define what Brownian motion is like, you have to mention that the gas particles will move in random zigzag motions with random speeds. If they ask you how come the particles move like this, you have to mention that it's because they will collide with other gas particles and change direction as they collide. So you can imagine it's like one ball knocking to another ball, change direction, then knock to another ball, then change direction, and knock and change. And they'll move in absolutely random orders. They will not have a predictable pattern. You get what I mean? Make sense, guys? Okay, copy this now.
Yeah, I'm done.
Okay, done. Let's move on to the next part here. Once again, we've already learned this in chemistry, but we can talk about it again, right? Pressure can be manipulated by two things. Either number one, the temperature, which we talked about just now, right? More frequent collision against the wall. That's the first one. And the second one is going to be volume. You can always imagine volume like when you're trying to crush a balloon. When you try to crush, before you try to crush it, right? The balloon, when you hold it on your hand, you don't feel like there's a lot of pressure. But as soon as you start crushing into the balloon, you can literally feel in your hand that the balloon is about to explode due to the increased pressure. How come there is an increased pressure? Is because before you crush it, the gas molecules are just like constantly colliding against the walls of the container, right? But as soon as you start compressing it, you actually decrease the space available for the gas particles. And because of that, they'll collide against the walls of the container more frequently. Once again, an increase in collision against the walls of the container causes the force per unit area to increase, which will ultimately lead to an increase in pressure. Okay, so if you look at the graphs, right, this kind of makes sense, right? The higher the pressure, the higher the temperature, the greater the pressure. But for volume, they are inversely proportional, meaning to say at high volume, there'll be low pressure, but at low volume, when you compress the balloon already, they'll have a relatively high pressure. So what I can do is I can just inverse the V, right? If I inverse the V to become 1 over V, I can get a directly proportional graph again, proving that this is inversely proportional. Make sense? Okay, copy this now. Done? Anyone not done drawing yet?
No, I'm not done.
Oh,
Okay.
okay. Okay. Last thing I want to talk about is how do we apply this Boyle's law formula here, which is P1 V1 equals to P2 V2. So let's imagine today you dive down into the swimming pool, right? And then at the bottom of the swimming pool here, you let down a specific gas bubble. Okay, when you let a specific gas bubble up here, it's obviously going to start floating towards the top, right? Do you know that when it floats to the top, right, the gas bubble actually increases in size? How come? Why does the gas bubble, when it was at the bottom, is relatively low, small in size? Then when it reaches almost the surface, the volume increases so much. What's happening?
Pressure is low. Def.
Very good. At the top region, on the surface region, what happens is the pressure definitely is much smaller, right? In a deeper region, the pressure is much higher. So I'm literally at the lower region now, I'm literally compressing the air bubble. But as it rises towards the surface, it becomes bigger because there's less and less and less and less and less and less pressure acting on it. From here, I can use Boyle's law formula, which is P1V1 equals to P2V2, right? So let's imagine like at the bottom here, I had 100 pascals. Okay, and the volume here, let's just say was 2 meters cubed. Okay, at the top for sure, the pressure is much less. Let's just say it's only 10 pascals. From here, I can find out how much is my volume already by applying 100 equals, 100 times 2 is equals to 10 times your V. Your V will definitely be 20 meters cubed. Make sense? Bro, I repeat again. So this formula can be applicable in this kind of scenario here. But you must be given 3 things out of these 4 things here, right? So in this scenario, I'm giving you 100 pascals initially at 2 meters cubed. 100 pascals at 2 meters cubed. Make sense?
Yeah.
Yeah.
Okay. So yeah, this is how this formula can only work if the temperature is constant. Meaning to say, right, if here, let's say it's 40 degrees Celsius, why is the swimming pool 40 degrees Celsius? But let's say it's 40 degrees Celsius. Here must be 40 degrees Celsius. If the question, which will never happen, you say that, oh, here is 30 degrees Celsius and here is 40 degrees Celsius, find the volume, cannot work. This formula cannot work. So you know how the question will test you this instead? The question will test you that in order for you to use this formula, what must be true? You must say that this temperature and this temperature must be the same in order for me to use Boyle's law formula. Make sense? Okay, copy reading now.